Okay, we're going to start talking about proofs today. I've mentioned it before, uh, but it'll make more sense when I show you. Okay, so in algebraic proofs, which you've kind of already seen, it's a nice way to go into proofs because you've done all this addition and subtraction, multiplication, and so on. Okay, the properties you have to describe what you do from step to step whenever it comes to proofs. Okay, so sometimes you're going to add to both sides of an equal sign. So the reason that you did that was addition. If you subtract from both sides of the equal sign, then that property would be subtraction. Okay? Multiplication, same thing. You multiply to both sides of the equal sign, and division is the same as well. You divide from both sides of the equal sign. Okay? But combining like terms is something you do to one side, right? Like if you have 3x plus 4x plus 7x equals something, then you add up to 3x, 4x, and 7x to get 14x, right? Okay, distributive you've seen before. It happens on one side, right? Basically, there's a number on the outside of parentheses, and the number on the outside has to multiply by every single thing that's on the inside, one at a time. So 3 times x would be 3x, and 3 times 4 would be 12. Okay, so these are reasons in a proof that we're going to see here in a little bit. Okay, once again, each one of these takes a step from here to here, right? So if this was the first line in the proof and this was the second line in the proof, then there would be a reason that you went from here to here. Okay, so what happened to this 2? Why did it disappear? Because we had to do what to both sides? We had to multiply the top by 2 on both sides. So that's why x is 14. You multiply this side by 2 and this side by 2, the 2's cancel over here and you get 14. So the reason for taking the step from here to here is multiplication. Okay, if x is equal to 5 and b is also equal to 5, wouldn't it be true that x is equal to b, right? Because 5 is equal to x and 5 is also equal to b, so wouldn't x and b be equal? That's called substitution because what we did is okay, we've got x here. Okay, so there's an x equals 5. So if I know that b equals 5, wherever I see a 5, couldn't I put a b instead? Wherever I see a 5, I could put b instead, right? Because they're equal. If they're equal, I can use them interchangeably, like running backs in a football game. Okay, so I see a 5 right there. So couldn't I put a b here instead? And that's what I did to get this. Okay, I substituted uh, for this 5. I substituted a b in place of the 5 because these are equal, so I can substitute. All right. Okay, so whoops. This is addition. Oh, excuse me. Anyway, basically what happened was that this one said minus AB and this one said minus AB. So how did we get rid of the minus ABs on both sides? Well, we had to have added an AB to both sides, right? And that's why it disappeared. So addition was the reason for this step over to this step. Okay, the minus ABs disappeared. We added AB to both sides. Okay, we know what this one is, right? This is simple, right? What did we do to get this step from this one? Well, of course, distributive. We distributed. Okay, so here, 3x and 4x equals 7. Now all of a sudden you've got 7x equals 7. What happened? Yeah, we combined the like terms, didn't we? Okay, on the same side, we combine the like terms, and that's what they call it. Okay, so 4x equals 16, then all of a sudden x is equal to 4. How did that 4 disappear? Yeah, we divided. We divided by 4 on both sides, right? So this is division. And then here, 3x plus 6 equals 12. All of a sudden now it's 3x. What happened to this 6? This plus 6? Exactly. We subtracted it away. We subtracted minus 6 from both sides, and you ended up here. If you had another step, you'd divide, right? Okay, so that's a bunch of steps that you can have in a proof. So we're going to talk about proofs. They're two-column proofs. One side is statements and one side is reasons. You always start out with a given and something to prove. This is the first step in the proof. The prove is the last step in the proof. So you start out with a given, a premise that you want to start with, and then you show what you want to prove. So you'll see this will make more sense if I put this up here. Okay, this is an algebraic proof. Okay, so simple because you already have an understanding of algebra and how to solve for equations, solve for x. Okay, so here's this. That's what's given. That always goes in the first step. Okay, what we're trying to prove, the very last step down here will be x equals -2. Okay, and so each one of these steps is going to be, there's going to be a reason for it. Okay, so we start out with the given. Simple. Okay, we put that there, and the reason for it, well, is given because that's what was given. That's the reason. So you have a statement and a reason. So what are we going to do first to this one? Just like you're solving an algebra problem, because you are. Okay, so you distribute, right? Okay, so now all of a sudden it looks like this, and the reason would be distributive, right? Okay, they did the distributive property to get this one right. Okay, so what do we do now? Okay, yeah, we could, the 9 and the 2, couldn't we combine them, right? And it would be 11 here. So this is what reason? Of course, combining like terms. Okay, so that's why we took these two. You have to look at it like this, okay? Here's a step from here to here, and we give the reason for this step. So we look at the first part and the second part and then figure out the reason. Okay, so now from here to here, what do you think they're going to do? Yeah, it's going to look like this. What did they do? Yeah, they subtracted 11 from both sides. Okay, so that was a subtraction step. To go from 3 to 4 was a subtraction step. So what are we going to do to go from 4 to 5? Okay, this is what they did. Okay, this is what we're trying to prove, but we don't write prove here. We give the reason for 4 to 5. So what happened from 4 to 5? Well, the 15 disappeared because you divided by 15 on both sides. So that was a division step. Okay, so there's the given. We started with that. And then what we tried to prove, we did. So we're done with our proof. Every step had a reason, including given for the first one, right? Okay, so that's an algebraic proof. Okay, so now I have to talk about reflexive, symmetric, and transitive properties. These are used in proofs as well. Okay, reflexive is kind of strange. If you have something, then isn't something equal to itself? If you have A, like 5, then isn't 5 equal to 5? Of course it is. That is the reflexive property, okay? The reflexive property states that if you have a number, then it's equal to itself, and there's a reason for it, especially later on in triangles when we talk about stuff. So that's one property. Okay, symmetric is when you switch sides, like if A then B, then B then A. So if you have something that is like x equals 2 and you need to, or you have 2 equals x and you want to switch it around to where it's x equals 2, this would be the reason, symmetric. Symmetric switches one from one side to the other, okay? And then transitive, we've already talked about this with syllogism. Syllogism is where the first part equals the second part equals the third part, so the first and third are equal. So if A is equal to B and B is equal to C, then these two guys are equal. A is equal to C, right? Okay, first, second, second, third, first, third is what is here. So those are 3 properties. Let's look at them in example form. Let's say we had reflexive, okay? So if you started out saying that you had angle T and you wanted to do the reflexive property, what do you think it's going to say here? If it's equal to itself, then what are we going to write here? If you said angle T is congruent to angle T, then that would be correct because it's equal to itself, right? And the reason that we can do that and create this is because of what property? Yes, the reflexive property, okay? So if you see this and then all of a sudden it's equal to itself, then that's the reflexive property. Okay, you can also do it with segments. Like if you had AB, then what could you write here? Of course, you can say AB is congruent to AB, right? And that would be by the very same reason, which is the reflexive property, okay? Next, symmetric. Remember, they switch sides, right? Okay, so symmetric is a switch sides. So if you have M is congruent to Y, then in the next step, you could switch them y is congruent to m by what reason? Symmetric. The symmetric property. If you say symmetric, that's good enough. You don't have to write all these property names down. Just symmetric's good. Okay, so m went to here and y went back over here. So they switch sides. So you can do it with angles, and guess what? You can do it with segments. So if AB is congruent to CD, then what would you do? Of course, CD is congruent to AB. Switch sides. And what reason? Symmetric. Yes. Okay, so that's symmetric. Now, the transitive property. Okay, so A is equal to B and B is equal to C, then A is equal to C. First, second, second, third, first, third. Okay, so here we go. If A is congruent to B and B is congruent to C, well, guess what you can say? If A is congruent to B and B is congruent to C, then guess what? They're all the same, really. A is equal to C. Okay, so that's what you would write here. So if you see this happen, then that's the transitive property. Okay, transitive. All right, sometimes they stack these, or sometimes they're in 2 or 3 different steps, and so it's hard to see or find them. But these two guys are the clue, because you have the B twice. All right, so substitution property can be tricky sometimes. Okay, so you can replace one with another. Anytime you got an equal sign, wherever you see A, you can put B. Wherever you see B, you can put A. Anywhere. So substitute is a good thing. All right. So say we got these segments over here. We got CD and AB and BC and AC, a bunch of segments. Okay. So I'm going to say AB is equal to CD. So this one is equal to that one. Okay. So in the next step, see this right here? If you have B in between A and C, can't you write AB plus BC equals AC? Here we go. This is the kind of stuff I was talking about. This is part plus part equals whole. So how can I write that? What is the property here? We talked about it last time. Okay, AB plus BC equals AC. What is this? Segment addition. Okay, segment addition. If you see a segment and it's got B in between there, and it doesn't say anything about midpoint or whatever, you can always say AB plus BC equals AC. And in proofs, it's nice to be able to create something. Okay, so that you can try to solve the proof for, switching things around, substituting, and doing whatever you need to do. Okay, notice that AB is right here. Okay, and then the next step, it says CD plus BC equals AC. Aren't these the same? These are the same, but these are different. How can we do that? How can we do that? Yes, we can do it because of this. Wherever I see AB, can I put CD instead? They're equal, right? So instead of AB, I put in CD by the substitution property. Substitution. I was allowed to substitute because these are equal. So wherever I see AB, I can put CD instead, so I did. Okay, this one's a little harder to see. Okay, how can we say this? It's another substitution. I'll just go ahead and tell you that right now. It's a substitution. Notice that the first part is here, right? This part on the other side is here, okay? Both of them are equal to AC, right? Like this part's equal to AC and this part's equal to AC. So AB plus BC equals AC. True? AC equal AC. Is that true? AC equals CD plus BC. True? So couldn't you take this whole mess right here and put it here instead? Because wherever you see AC, can I put the other side in place of AC? Well, here's AC up here, right? So I'm going to take this and shove it up here, and that's what you see here. Okay, so I actually substituted this part in for AC because this part was equal to AC. If it's equal to AC, then you can plug it in for AC. So I did, and that's what we have here. And now I could go on and subtract the BCs if I wanted to. Okay? All right. Next. Here's an actual proof. I'm saying that MN is congruent to PQ. I'm also saying that PQ is congruent to RS. So I want to prove that RS is congruent to MN, which obviously makes sense that it is. Okay, so this is given. So I'm going to start it. Okay, here it is. I wrote it in the given. Okay, so what is the reason for the first one? Of course, it's the given, right? Now, this is that strange one we talked about, congruent segments. Okay? So if the segments are congruent, then their measures are equal, right? So remember I talked about taking the hat off? Okay, so we're going to take this little line, the squiggly line, and this little line segment as well, and take them off on all of these and put it like that. Because if the segments are congruent, then the measures are equal, right? Okay, so I did that, and now I'm going to do transitive. What's transitive? Do you remember? Yeah, first, second, second, third. So what do you think is going to be here? First, third, right? So it'll be Mn is equal to Rs. The PQs kind of cancel out actually, and then Mn is equal to Rs. So that's the transitive property. Okay, so what happens from here to here? All of a sudden Rs is over here and Mn is over there. Do you remember that property? What was the name of the one where they switch sides? That's correct. Symmetric property. Very nice. Okay, symmetric. Now, I'm going from the measures back to saying, putting the hat back on and saying that the measures, then the segments are congruent, right? So if the measures are equal, the segments are congruent. And that's the same definition we had up here, isn't it? We took the hat off and brought it down to measures level. Now I'm going from measures level and putting the hat back on, which making it segments again. And that's also the definition of congruent segments, right? Took it down, raised it up. Okay? Went from segments to measures and then measures to segments. Okay? So we just did a proof. Okay? We proved this, which is what we were trying to do. Okay? All right, so L is the midpoint of Km. Okay? Obviously that we know that those parts are equal. Eventually we're going to probably use that in this proof. Then we also have been given a second part that Lm is congruent to AB. So they want us to prove that KL is congruent to AB, which makes sense if it's a midpoint and these are equal, right? So this would have to be true. But let's write the proof, okay? So we're going to start off with one part of the given, one part. L is the midpoint of Km, okay? And the reason? Of course, it was given, okay? It was given. So if L is the midpoint of Km, then what do we know is true? Remember the definition of, I don't want to say it. What does this do? What does a midpoint do? Right? If this is a midpoint, what's true about these two parts? Yeah, they're equal. So couldn't I write KL is congruent to LM? This part is congruent to this part, right? Okay, so here's where a lot of people screw up and say definition of congruent segments. No, 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 no. The previous step has a word in it. Usually if it has a word in it, it helps you to know what the reason is going to be, okay? So if it's a midpoint, it creates two congruent segments. Guess what? That's the definition of midpoint. If it's a midpoint, it creates two congruent segments, okay? Now here's where a lot of people say, uh-oh, what's LM is congruent to AB? I don't know anything about this. Well, look up here. There it is, okay? They're giving a second given. Okay, you can have a given later on because if there's two givens, then you can use them both at once sometimes and sometimes not. Sometimes it's better to put it down further. So LM is congruent to AB, that was a given. And then we were trying to prove this, and we were lucky to know that this is the last step. So KL is going to be congruent to AB because that's what we're trying to prove. And this is a nice proof because we don't have to we don't have to figure it all out on our own. We've got spaces and stuff like that. It makes it nice. Okay, but how in the world did I get KL congruent to AB out of these two lines? These two lines. Okay? Well, here's what I notice. See that LM and this LM? Right? They're the same, right? And then KL and AB, isn't that here? So isn't that like a first, second, second, third, first, third? Right? Do you remember the property that allows you to do that? Transitive. That's right. Transitive is the property. Very nice. All right, so we proved it. That was the reason. Here we go. One more, I think. I think this is the last one. Okay, AC, which is this part all the way to here, is congruent to BD, which is this part all the way to here. We want to prove that AB is congruent to CD. This part is congruent to this part, okay? So given, right? We put that here. This is the given. You remember the reason. We always, that first one is given, right? So they gave us this, so we write down given for the reason. Now, if it's the definition of congruent segments, what am I going to do to this? Okay, what am I going to do? Yeah, I'm going to take the hat off and bring it down to its measures and say AC is equal to BD, right? By the definition of congruent segments. Okay, so segment addition, all right, segment addition, is part plus part equals whole. And they want stuff to be created so that you can get down here and do this stuff. So the two segments that were brought into the picture were the ABC one, right? So I wrote it backwards so that you can get used to seeing it weird. First part plus second part equals to AC, the whole thing. That's this one. And then the other one is going to be BCD, right? So this part plus this part equals to BD, the whole thing. We'll write it backwards as well. Okay, so segment addition allows us to make equations like that. Whenever you have something between two other things like this in segments, part plus part equals whole. All right, so basically this part is set equal to here in this segment in number 4. Okay, so we have to be able to, the reason that we have to be able to do that, but AC and BD, the last problem we did, these weren't equal, were they? Or they were equal. They were exactly the same thing. I'm sorry, but this one, these aren't. AC and BD don't seem to be equal at all, unless you look up here. It says that AC is equal to BD, right? So if these two are equal, and this is equal to this one, and this is equal to this one, then can't you substitute, say, this one into this one? Okay, let's say it again. This one is equal to this one. This one is equal to this one. So wherever I see this one, I can put this one. So I moved it to the front, and that's what you see here. Okay, and that's substitution, right? We substituted in. Now, to go from here to here, what disappeared? Yeah, the BC's disappeared. So how do you get rid of two BC's that are positive? Yeah, you got to subtract them away, right, if they're on either side of the equal sign. And so we did that, and then this is what we're trying to prove, so we can just write that in there, right? And what do you remember what the property would be here to take it from the measures back to the segments, right? Yeah, definition of congruent segments again. Okay? All right, well, y'all have a great day. I got to kill this thing, got to kill it, kill it, kill it, kill it, kill it.